So hi, my name is Abdullah Keskin, and now I will make a short presentation on my pattern recognition term project. So let's get started with the contents. First, I will give a general overview of the SVM framework, formulation, and the methodology, and then I will focus on two different SVM approaches with two different loss functions. Then I will focus on the outlier problem and compare these two SVM approaches, and then I will finalize my presentation with the results and conclusions taken from my experiments on different datasets. So let's get started with the general SVM framework. Here you can see two classes, and there is an optimal separating hyperplane. What SVM tries to do is to maximize this margin and obtain a optimal separating hyperplane separating these two classes. And here you can see, as you see, that it's a linearly separable data, but in general it's not, and in general we do not know if it is linearly separable or not. So inserting those loss of the correct and misclassified samples, we obtain a final cost function of the form given here with a c given parameter and also given loss function for misclassified samples. And we are trying to optimize this function and obtain weight of the optimal separating hyperplane. This is the general idea behind the SVM. And now let's focus on this loss function, which is going to be extremely critical for our project. So this is regular SVM loss function, inch loss. As you can see, this is the plot of the loss function with respect to distance from the boundary optimal separating hyperplane. And it's a convex function without any boundary and is it optimized due to the convexity of the function. And what it does is the penalizing the misclassified samples, and it penalizes the incorrectly classified samples, but it also penalizes the samples which are correctly classified, but they are still close to separating hyperplane, which actually what SVM tries to do, trying to maximize this margin by means of optimizing loss function. And if you look at this figure, this is a wrong misclassified sample, and the loss of this sample is higher than this one, and also it's higher than this one. This is what SVM tries to do with this loss function. So if you focus on the new SVM or brand new SVM, which is the one mentioned in the paper, my project implementation, which is L01 SVM, its loss function is given here. It's a natural loss function for binary classification problem, as you can see here. If a sample is misclassified, directly assign a loss or penalty as 1. And it doesn't take the distance from the optimal separating hyperplane into account. It directly assigns loss of 1. And if it's correctly classified, again, without depending on the distance from the optimal separating hyperplane, it assigns 0, no loss. It's a binary loss in overall. So if you focus on again this figure, for example, this is a misclassified sample giving loss 1. This is another misclassified sample, it also gives 1, and it's valid for this one as well. And these are the correctly classified samples without any loss. So let's focus on the outlier problem. Again, we have two classes, and there's an outlier here. If we use the regular hinge loss SVM, this is going to give lots of loss. Okay, it's extremely away from the optimal separating hyperplane, and even we don't even know this is going to be the optimal separating hyperplane when this cost function used, this loss function used, because this may disrupt the behavior when such a loss function is utilized. And it's going to, with this loss function, regular HSVM, it's going to insert lots of loss, and it may disrupt the overall cost function behavior. But if we use a L01 loss function, soft margin, it's going to give only loss of 1, okay, nothing more than that, because it doesn't take the distance from the optimal separating hyperplane. And in this case, we have one outlier, and consider having lots of outliers, noisy data, and you have lots of outliers. It may, using such a loss function, may prohibit you from obtaining a optimal separating hyperplane which generalizes the data well. Okay, it may disrupt the overall behavior, and if you use such a loss function, you may somehow eliminate the effects of such outliers. And let's see if we managed such a optimal behavior or not. First, I will focus on the experiments with or data sets with having features whose values are continuous or real values. We have two different experiments actually here. Actually, I have more in my paper, but these two are the ones I have taken my paper, my experiments. In general, we see that for accuracy, our brand new SVM performs well in all cases. This is the outlier ratio here given, and even we increase the outlier ratio, we still have our L01 SVM performing better. And at the same time, while we having a high accuracy, we also have lower CPU time, which is another important parameter, and also we have a small number of support vectors compared to HSVM, which is also good because this is the memory efficiency property of our brand new SVM. This is also valid for another dataset that I implemented my algorithm. Here we do not observe a very important difference, but still L01 SVM performs well in the accuracy case, and also for the CPU time and the number of support vectors, still our brand new SVM performs better. And now let's focus on the data sets having integer values, necessarily non-continuous features or discrete features. For the first results, we still observe, L01 SVM performing better, but for the uh, other case, experiments on another data set, actually we have some oscillatory behavior. Starting with L01 performing better with zero outlier ratio, and then uh, these things change a little bit when we increase the uh, outlier ratio more, and then again 01 performs better. And this is also valid for CPU time, but in general, average, still 01 SVM performs better in terms of CPU time, and this is also valid for a number of support vectors. For the integer values, still L01 somehow performs better, but I think this is not extremely reliable. To have a better understanding of the uh, algorithm on discrete features, we need more experiments because this is not a extremely valid result if you ask me. So in overall, we have seen that our brand new algorithm, our brand new loss function and SVM formulation performed better in terms of accuracy, number of support vectors, and also the CPU time, especially for the datasets having continuous valued features. But for the discrete features, I can't make such a claim actually. Still, we have nice results, especially in terms of accuracy for some specific data sets. But to validate the performance of our new algorithm, or to have such a claim that our new algorithm, new loss function performs better than the regular SVM on datasets having integer features, discrete features, one needs to perform more experiments. So thank you for your attention.